All right, I guess I'm up for a quick vignette on density projection here, or illustration. So I'll share my screen, and then, all right, so related technique that is a bit of a pivot though from the super cool work Iadine was just talking about is density projection. And the discussion before I get started is going to focus on problems involving parameter uncertainty, but these techniques have also been used to work on POMDPs, which Iadine is going to introduce later this afternoon. So, and they have broader applications than just what I'm going to illustrate, but I think we're going to try to draw a connection to what came up earlier in the workshop. So to get started and building off of Paul's last presentation, in standard AM problems, we have a belief distribution over an unknown parameter, let's say, and where our beliefs are going to incorporate any information in principle useful for updating, actions, observations that are useful, and also hyperparameters. And to get models to go here, we need an update rule for the hyperparameters. So once we receive new information, what is our new hyperparameter that summarizes our beliefs about the unknown component of the model? And classical AM models use assumptions that lead to conjugacy. So this belief distribution remains in the same family. So you can have closed form update rules for the hyperparameters. Conjugacy is really useful and highly encourage you, all else being equal, if you have a problem where you think it's reasonable to put together a model that has that property. But it's fragile and it can break down quickly when you want to address some interesting components of a given problem. And when you have that breakdown, you run into a severe cursive dimensionality. Suddenly you need to, in principle, account for transitions among many different types of distributions, and you run into problems solving the model. So one solution to address this is density projection, which the idea is as follows. You have a true posterior for, let's assume, a fixed parameter to keep things simple. But it's not going to have the same form as your prior necessarily, so you're going to approximate it with typically a parameterized density f hat here. And so as you might guess, we want this f hat to be as close as possible, subject to the structure of the approximation, to the true posterior that you can compute with a variety of methods depending on your application. And so the method we're going to use to determine the goodness of the fit and in fact find a good approximation is what's known as Kullback. We're going to minimize what's known as the Kullback-Leibler divergence between the true posterior and your approximation. And that takes the following form, the divergence, and it's going to be the expected log likelihood ratio that we're trying to minimize here. We're taking the expectation with respect to the true posterior here. So it turns out that a really convenient and nice property of this minimization is that if you're using an exponential family distribution as your approximating density, like the gamma, normal, log normal, this minimization, which looks like potentially a gnarly numerical operation, has a closed form solution that you can compute quickly, and it's to match the sufficient statistics of your approximating distribution with those of the true posterior. So if you have a normal approximation, This can involve matching the mean and standard deviation to the simulated posterior or computed posterior that may not be itself normal. So this is very helpful, and it kind of restores the flavor, I guess you could say, of these classical conjugate models, but with an extra layer of computation. So I'm going back. I've actually really liked, we've been able to connect a lot of our examples through the whole webinar. A couple papers popping up, like the CSIRO study Iadine did. So I'm using Mike's paper with Jim Sankiriko again, and those of you who are with us, I guess it was 2 days ago now, will remember the essentials, and I'll try to repeat them for everybody's benefit. So this is an optimal harvest model under uncertainty, where the goal is to optimize the value of the fishery, or the expected present value of fishing profit. But the illustration I'm about to do, I'm going to assume no harvest to keep things simple. Now, the source of uncertainty is concentrated in, or limited to, the following. You have an initial beginning of period population that produces juvenile fish according to this simple scaling factor here. And those juveniles survive, and the source of stochasticity in the model is, I'm going to talk about how it was set up before, but the full model that Mike analyzed, it's a binomial process. So the number of produced juveniles each is, you have with a little rounding here, you have Z trials, of which you get K successes. But the probability of success is, as I'll explain a little further in a moment, is no longer fixed. It's itself a dynamic variable in what's called a hierarchical model. So I'll circle back around to this a couple times, but my way of explaining it is that it's more realistic in many contexts to assume more complex relationships determining stochastic outcomes, and the conjugate model that is a simplified version of what they analyzed. It leads to unrealistically fast learning, and I think arguably too simple of a stochastic process for the population dynamics. Now, survivorship each period is generated as a draw from the another, I say another because a beta will come up in a different form for those that remember the first model, but it's going to come up as a draw from a density. So the probability itself of survival or survivorship is going to be a draw from beta. And we don't like to throw like 3 or 4 different ways of parameterizing a density at you, but I'm going to have to do it to keep keep consistent with the paper. So we're going to have a mean and a concentration, which is a particular measure of the spread around the mean, you could say. And we're so the I guess I'll jump ahead and say we're going to assume that uncertainty is going to come in. We're going to assume that the concentration is fixed and known to the decision maker, but we're learning about this S bar. So that's not I think a hugely unrealistic assumption at all. You know, you could think of it, we have some information about the regime generating survivorship, but we're uncertain about some component of it. Population dynamics have this Beverton-Holt form, and we're going to still have these hyperparameters, but that we're going to model beliefs with, and I'll explain. I'll emphasize sort of how this differs from the first example we went through. But the paper goes into how, if you attempt to compute the Bayesian update of beliefs about S bar after observing K successes, in a given period, it's no longer beta. You lose that conjugate property. And so density projection restores it in a sense so that we can have a ultimately updated beliefs across periods staying within uh, the same approximating beta family, which is very important for making this model feasible to solve. So again, I was trying to draw a connection to the basic beta binomial model I presented the first time, so people remember this. We have so in contrast to what I'm about to show and explaining the full version of this model, before the true probability of survivorship was fixed, and we were learning about that. But now, as I'll show, we're generalizing it, and this is not fixed, and we're learning about the process that generates those survivorship probabilities. So what I showed before is a typical pattern of your beliefs evolving, your point estimate and confidence around that over time as you get more data. So I'm going to show that again for the full model that I coded up, the dynamics that are under the hood of Mike's approach. And I'm going to show a run here from a initial prior around, you believe this S bar, which has a different interpretation in this context, is 0.5 initially, but it's actually higher. It's the true survivorship generating beta mean is 0.8, and we have a true concentration. And so an important point here is that you of course you don't directly observe these these stochastic survivorship probability draws, right? What you do observe is the relationship between initial juvenile production and juvenile survivorship. So I've generated this chain of the process again without harvest, and I'm going to show it through period t equals 10, but starting from a period at 3 where there's some, you needed a couple periods to actually generate a observation of survivorship from an initial population. So beliefs have already kind of crept towards the true hyperparameter, the true parameter model. This is not a hyperparameter, although the hyperparameters are representing beliefs and they're evolving over time. So I'll flip back, my bad, so you step forward, forward. And so this, you can see how this kind of restores that same property of being able to, in a parsimonious way, track the dynamics of beliefs in addition to physical state variables, and to construct the simulation you need to generate the realized but unobserved survivorship probabilities. So one property of this that I like as a nice illustration of the use of density projection in this context, and why there was interest in this hierarchical model, is that with the simple beta binomial model, with this many trials, where the population is this high, you can have very fast, when I was playing with this, you can have, particularly when the population is very high, you can have very fast convergence, unrealistically fast, where you've kind of resolved the mystery of this fishery in just a handful of periods. And that was the real impetus, I think, when they were working on this, to pose the model this way and generalize this framework relative to some classical papers. So I encourage you to read the paper, but I want to riff on it and talk about some punchline results that connect to some of our earlier discussions. So what they found is that gains from active adaptive management, so the whole framework there was put together to solve an AM problem for the optimal harvest policy, compare it to no learning and PAM approaches. So what they found is that gains from active adaptive management, the optimal solution to the beliefs state MDP, was largest when the stock was depleted and initial productivity is believed to be low. So I'll expand on that point here in a minute. But this is one context where Mike was saying that you know, this is one of these early 2010s pieces of research where because I think the way he put it well, this was one example where sort of taking a really broad brush average perspective, because the PAM and AAM solutions are doing pretty similar things in most cases, but I'll when I talk about the figure I'm showing here, I'll unpack this. And getting similar types of information, it's a case where an expectation AAM does do better and it is the best solution, but the gains are not tend to be small. So what am I showing on the figure? So this is comparing the no learning model and then AAM and PAM. So we're all familiar with those acronyms. And so where you tended to see qualitatively significant gains from active adaptive management is allowing the population, so the right-hand panel shows the per period average population over time. And notice how under AAM, for this case where you have a low productivity prior and a low initial population, you think that the stock is not that productive, although there's some uncertainty about that, meaning survivorship is going to be low, the draws on average, that's what you initially believe, and the population is low. Then the AAM policy, it's allowing a bigger population over time, sacrificing profits up front to allow rebuilding faster, and then ultimately with better information making better decisions to have more profitable fisheries management in the future. So sometimes um, the way in which an AAM solution explores and gains information is by doing nothing and allowing, for example, a depleted stock to rebuild and generate information that speeds learning. And so I think that's a finding that I really liked from this paper. This methodology, there are a few antecedents, but Jo and her co-authors have a nice paper in IEEE that describes how density projection can be used in belief MDPs, and then the source paper again that Mike did is shown here. So I see lots of chat content, and but I think what I might do is do we have like 15 minutes, everybody? Is that the roughly? We don't have to take the full time, but I think we had talked about having a maybe like somewhat more than 5 minutes just to.
I think we're actually at time now.
Oh, are we? Okay.
At 45 minutes after the hour, so we'll have to wrap up in probably a minute or so.
I have a question I want to ask, which about this model. Can you go back to the model? Maybe I don't understand what was what at the beginning, but what is the order of events in this model? You have a state equation, like a dynamic equation like that. Yeah, that model. Is that the harvest? Yeah, which way does it come? Harvest comes after the birth, and then the.
So no harvest for illustration. Harvest is from the end. You harvest off of this amount of the stock that's generated after the stochastic.
And so what is this? What is the psi there?
That's just a parameter.
No, but I mean, I meant like, what does 1 minus psi do? Is that just the survival, or what is that?
Yeah, it's natural, accounting for natural mortality, I think, of the initial beginning of period stock.
So it seems like to me then what you're doing is you're having juveniles being born into that class, but those juveniles are not subject to that same survival as the adults.
Yeah, I think so.
The order of the events doesn't, I don't know about that, because once you put something in the class, Yeah, I mean, did the surviving group did they, which one happened first? The
Maybe
surviving?
Mike should have to answer for what he's done here.
Anyway, I
You know,
think
I'm not
the
responsible
order
for
of events there is
this.
a little
I was just using his illustration.
Yeah, okay, the order of events. Okay, well,
It's
maybe
quite fun to watch Dave twist
I
in
can ask
Suzanne's wind
Mike
here.
that later, but I mean, the order of events.
For once, it's not my fault. You know,
Oh,
I'm giving a seminar, and it's not my
Right.
fault.
Okay.
Mike, do you have a quick answer?
The short answer is that the juvenile mortality is wrapped up in the stochastic binomial process. So you've got capital N adults produce Z juveniles, and then only K of those Z juveniles survive
Right.
as part of a stochastic binomial process.
I see. And then somehow but the tricky part is when you put them into the adults, they transitioned into adults after the adults survive, because the order makes a difference. You didn't
Yeah, so the order of events here is really at the beginning of the period, you have capital N adults. They
Yeah.
produce a bunch of juveniles.
Right.
And then both adults and juveniles undergo some survivorship or mortality process.
And then you add them in together.
And then they aggregate together into the
Okay, so
adult
basically,
population for the
yeah,
next
see
period.
The fact that they're separated and doing their survival, then you stick them back together. Okay, I got it.
Yeah.
Okay.
Cool.
Thanks.
Well, I apologize, everybody. I thought we were going to the top of the hour, but we do have the Mike is right. We got the break now. Were there any, I saw some chat activity. Did the other instructors kind of knock that out, or is there a question? I guess we're pretty much at time, so unless there's a quick question we could get at, we should probably wrap up.